We now need to consider how to scale from individual point-based measurements of precipitation to larger areas. In many cases, we can't rely on remotely sensed satellites or radar for this because it's simply too inaccurate. Point-based precipitation gauges remain the most accurate way to measure precipitation, but we frequently don't need to know about precipitation at a point, but rather over an area, for example, a catchment, in order to do mass balance. So we're going to talk about a few different ways to do this kind of scaling, and I'll note that these are not only applicable for dealing with precipitation, but the methods that we're talking about would also be suitable in some cases for averaging things like soil moisture over a larger spatial area or aquifer properties. The absolute simplest way is simply an arithmetic average. Consider some catchment that we're looking at from above, and it has some drainage network in it. This is the catchment that we're interested in. And let's say that there's a bunch of precipitation gauges that are kind of scattered about randomly here. So the easiest possible way is to say, well, these are the closest gauges. Therefore, the average precip, which I will denote with a capital P with a bar over it, is going to simply equal the precip recorded by these gauges the average of them. So sum them up and take their average. So that's not super complicated, but it may not be the most accurate way to do it. It kind of ignores, for example, how far away these are. There's no real weighting that's applied. The next method is slightly more complicated, and it's known as Thiessen polygons. And the idea here is that precip at each point on the landscape is assumed to be best represented by the nearest gauge. And so we need to figure out a way to determine what is the nearest gauge at any particular location on the landscape. So let's consider that we have some gauges that are spread out across the landscape. And Thiessen figured out how to do this graphically, and there's a recipe for doing this. So the first step is to create a system of triangles, and specifically create this thing known as a triangular irregular network between all of the points. And so you can imagine drawing straight lines between these points. Where each point is a particular gauge. And the question is now, which area in this landscape is closest to this point, not one of these other points? And the way to do this is to then take step 2. Step 2 is to draw perpendicular bisectors. And in doing so, you will outline an area which is closest to this point and not to any others. So a perpendicular bisector. The bisector is the halfway point and it's perpendicular. So I'll denote that with this little triangle here. I have a bunch of these in here. And they should, if I had done this correctly, they will all meet at the same spot in the middle of these triangles. Oops, I'm missing a triangle here. And as a result, we get this shaded area in here. And the idea is that this shaded area, any point in this area is closest to this gauge compared to any of the other gauges on the landscape. If we were to describe the total area A, and then describe in here this point as being precipitation gauge G, and this being little area G. The average precipitation is going to be 1 over the total area plus the sum as G goes from 1 to however many gauges there are of those little areas times the precipitation in each one. So this is a weighted average across the landscape with this Thiessen polygon method. One of the issues with both of these is that they don't contain any other spatial information other than the horizontal distribution of gauges. And in many catchments, we know that, for example, precipitation increases with elevation. So the final method that I'm going to talk about is known as the isohyetal method. And isohyet is a contour line of equal precipitation. So I'll write that, contours of equal precip. And so if we again consider some catchment here, and then we consider precipitation gauges distributed throughout it, instead of applying one of these methods, if elevation increases systematically in the headwaters of the catchment, and we suspect that there's systematically higher precipitation up here, say that this gauge records 15 inches a year, this one is 16.5, this one is 17 inches, we could draw contour lines of equal elevation, or of equal precipitation. So I'll draw a contour here, that's the 15-inch a year contour. We'll draw another one here, 16, and then we'll draw another one here, 17. And similarly to this method, we can now outline particular areas of the catchment that fall between these two different amounts of precipitation. And if we call this A sub I, and it's got an average precipitation, P sub I, again, the average precipitation is going to be 1 over the total area of the catchment, big A, plus the sum from I equals 1 to M, or however many zones there are, of the area in each zone weighted by the precipitation amount in each zone. So it's another weighted average, but in this case it's taking into account these spatial gradients that may occur in the catchment.